Hello everyone. Today we are going to break the mystery of mobius function. It might seem intimidating initially, but at the outset it feels awkward or strange to define such thing. As we get closer and closer to the properties of it, you will get accustomed to it and you will start deriving properties using it. Let's see what it really means. So by definition, mobius function that is denoted by mu of n is a arithmetic function that takes in natural numbers and gives you integers, but only three different type of integers. It gives you 1 if n equals 1. It gives you 0 if n is not square free. That is, a prime squared divides the number n. And it gives you -1 to the k if n is of the form p1, p2 till pk. So this means that n is square free and it has k prime factors in it. That's it. This is the function. So might seem a bit strange or unusual initially. Why such definition? Three types of definitions, right? Let's see one of the beautiful properties of mobius function. The sum of mu of d, where d is a divisor of a certain number, equals 0 if n is greater than 1 and 1 if n equals 1. This is such a powerful tool which we are going to use repeatedly in our forthcoming discussions. This makes mu function inevitably powerful. Let's prove this. First, notice that if n equals 1, mu of 1 equals 1 and we are done directly. But if n is greater than 1, by prime factorization, I know that it can be decomposed as p1 power alpha 1, p2 power alpha 2 till pt power alpha t for some primes p1 to pt and for some exponents alpha 1 to alpha t, which are some whole numbers. Now, considering this function summation of all divisors, the value of non-square free divisors will go to 0. So they will just annihilate. What just remains will be the square free primes as well as 1. So let's recollect. In the definition, mu assumes 0 if it is not square free. So let's disregard all the non-square free divisors. This gives us with mu of 1 plus mu of p1 plus mu of p2 and so on till mu of pt. This is primes taken 1 at a time. Then primes taken 2 at a time will be mu of p1 p2, mu of p1 p3 and so on up to mu of pt minus 1 pt. Next comes primes taken 3 at a time, 4 at a time and so on. All of these are going to get added. So again I'm reminding you and just disregarding the divisors that are not square free, because their value is going to be 0 and they will annihilate from this in the sum to 0. Okay, let's write mu of 1 as 1, whereas mu of p1 to mu of pt, all of them will be -1 because k is an odd number in this case. The number of primes in each of them is 1 in number, which is an odd number. So -1 power 1 will be -1. -1 occurs how many times? Well, t times. In fact, t choose 1 times plus -1 whole squared because there are 2 primes each time. And how many such expressions? T choose 2. I have t primes. I choose 2 primes out of them. T choose 2 is the number of ways to choose 2 primes out of t given primes. Like I consider them as t different objects. Then -1 whole cube times t choose 3. You see a pattern, right? It goes up to -1 power t times t choose t. The value depends on the parity of t. Okay, I'm just slightly tweaking the first term to write all the numbers or all the terms of this expression in a nice order. -1 power 0 times t choose 0 as 1 plus -1 power 1 t choose 1 as the second term, -1 whole square t choose 2 as the third term and so on. Now this is just the binomially expanded expression of 1 plus minus 1 whole to the power of t. This gives us 0 power t, which is 0. Awesome, right? That sum of the mu values for divisors equals 0 for any number except 1. If it's 1, then the value is 1. But how does this apply to such properties or like other properties? Because even mobius functions are used in research. So let's first understand one fundamental thing. I always appreciate its application in summation function. What is a summation function? Consider an arithmetic function. Arithmetic function means a function that takes integer input or natural number input and gives you some complex number output. So f from n to c is an arithmetic function. Now the summation function of lowercase f, usually denoted by uppercase f, equal the function evaluated at all the divisors of a particular value. So n here. This one is called the summation function. Summation function of f. So if you are aware of the summation function of phi of n, that is Euler's torsion function, phi of d divides n is just n. So they are quite interesting. By the way, Euler's torsion function is the estimate of number of numbers that are co-prime to a particular number and less than or equal to that. Okay, so how is it related to Mobius function? Finding summation function from some arithmetic function is this way. Just take the sums of the actual function evaluated at the divisors of a particular value. But given a summation function, can I retrieve back my original function? Yes, indeed you can. That is using the Mobius function multiplied with the summation function. Mu of d times capital F of n by d, where d is the divisors of n. In fact, the proof of this is just 4 or 5 lines maximum. So the proof is just d divides n mu of d, and capital F, the summation function, is replaced with lowercase f of k, where k divides n by d. Now I am going to take mu of d inside the summation and I get f of k, d divides n, k divides n by d. Now the same summation is evaluated in a different way by reversing the order of summations. First we consider the summation over k, that is for a fixed k, f of k is fixed. I am going to sum it over the Mobius functions. So k divides n, summation, how will I know the limits or the constraint on d? Well, the constraint on k and d together is provided to us. K divides n by d, or in fact this is equivalent to kd divides n. So I can now say that d divides n by k for a fixed k. That's how d runs based on the value of k. So I fix the value of k and run d. You have mu of d times f of k. So this is like if you are given 4 dots per row and you are given 3 rows of such configuration. How do you count? Either you count row wise. Each row has 4 dots, totaling up to 12 dots in number. Simple. I can also count it column wise. I have 3 dots in each column, 3 4s are 12. I am using that analogy here. The summation can be taken in one order, like row wise. Now when you invert or reverse the order of summation, it just means the summation is taken column wise. F of k is constant as d runs over the divisors of n by k. So I am going to pull it out of the summation to get d divides n by k mu of d. And well, we know that this is 0 unless n by k is 1. So all of the terms are going to nullify except when k equals n, right? So when k equals n, I have mu of n and the summation is 1. So f of n times 1, which is f of n. So therefore, starting capital F, I derived my original function small f. So this is called as Mobius inversion formula. It's a very important idea in analytical number theory. So by this, we know that the summation mu of d times n by d, that is the Mobius inversion of n, d runs over the divisors of n, should be my Euler's torsion function. And since n is a constant, we get another nice way of looking into the Euler's torsion function. That is, the fraction of numbers coprime to n equals the sum of Mobius functions by the corresponding divisor. And isn't that quite interesting? Because you get the fraction of coprime numbers for a particular number. So it sort of peaks when you have prime numbers, because phi of n equals n minus 1 for prime. Not only this, one example of Mobius function application, it is also applied to find the sum of primitive nth roots of unity or primitive roots modulo of prime and so on. You can refer to the book in Analytical Number Theory by Apostol for more such applications. We will discuss more such ideas in the next video. Thank you everyone. Bye.